All right. Now our open loop, the pause for that system eigenvalue is, so that's my pause. If I plot here, and this is real axis, this is imaginary axis, then my pole there is plus this my I, and this is my minus I. So that's my pole, and that is my eigenvalue too. That means if I have, that's my that's equal to U, and if I write the eigenvalue is lambda squared plus 1 equal to 0, that's my pole. If I put this equal to 0, that implies lambda equal to plus minus I. Okay, that's my pole, an open loop pole. And that's my closed loop pole here. Okay, that's R, this I. That's my imaginary, this is my real part. That's 0.5, so I have a 0.5 here, assume this 0.5, this 0.5 minus, and then I have 0.886i, so this is 0.866i, so this is 0.886i, alright, and so I have that, so this is my pole, my closed loop pole, and this my closed loop pole, so that's my closed loop pole, and this is also this minus 0.886i. Alright? Now I move, after I have U equal to that, U equal to F1 W plus F2 W dot. Now from that, then I have U is equal to minus W dot. Alright, if I have that, then my W double dot plus W equal to F equal to U, that equal to minus W dot. So my closed loop is plus W dot plus W equal to 0. Alright? And that give me eigenvalue, plus 1 equal to 0. And that give me this. Lambda equal to minus 0.5 plus minus 0.866i. You'll be able to see it from this side. All right. When I give the closed loop, when I give the U, that's my control force U. That control force U is minus W dot. Then I move my pole. This is my open loop pole. I move from there to there, and this from here to there. As I move. And why I want to do this? In the system, we know that all this left-hand plane, this left plane, this is a stable plane. Now, I think if you look at this all in here, this is the stable plane. All right. So here, if you have in the imaginary axis, that means this is what we call. You remember that? This is still stable, but this is no damping. This is in this axis. in the imaginary axis, if you have a pole on the imaginary axis, that means there's no damping. Right? This on the imaginary axis. So this one, no damping. Right? If I put on the left-hand plane, then I have minus 0.5 here. In the real part, I have, this minus 0.5. This minus 0.5. That is minus 0.5. So I move the pole from I to minus 0.5. So this point is minus 0.5 plus 0.886i. And this is minus 0.5 minus 0.886i. Right? And because I have real part is negative, so this one, this system, in this one, we call asymptotically stable. So, my cross loop design, I give the pole. I say, this is my desired pole, my desired pole. I come back to compute what kind of U I get. And if I give this kind of pole, my U will be just minus W dot. That means my original open loop system is not asymptotic stable. My original system, open loop system without U, that is no damping. After add this feedback, U, then I get a damping. Understand? So this is why my closed loop system is minus 0.5 plus 0.886. Okay. Now, if I give you a question, I say, all right, if I want to move my pole from the stable plane to the unstable plane, this is all this on the right hand side, this is unstable plane. If you say my desired eigenvalue, my desired pole is unstable pole, can I move that from the non-damping pole to the unstable pole? The answer is yes, you can do that too. Only some crazy guy will do that. But you can do that. The method-wise is okay. Well, it's not funny, but if you know that the phytoplane means the military plane. The military plane, they are really unstable, you know. So you can do faster. But anyway, for this kind of method, we always like to move from a no damping system to a with a damping system. That means after we give the feedback like this, my system become very stable. So this is a very stable system. We call asymptotically stable. Understand now? Okay. So that's the purpose. The pole placement technique assume in our closed loop pole first, then you come back to do this. And then some other method, you don't do that. Some other method, it just gives you, and later on, maybe next month, we'll talk about optimal control. Optimal control will be a little bit different from this. You don't know the closed loop pole. You know something else. Okay, but now this is the continuous time system. See, this is continuous time model. Now the question is, how about the discrete time model? All right. So this design is just like this. Just like this. So if I have the W dot measurement, then you can just, your feedback just like this. If you have a W dot measurement. If you don't, then you need an observer. If you do have a measurement, this design is equivalent to this just feedback, direct velocity feedback. Understand? So for this case, if you have velocity measurement, then you don't need observer. If you don't, then you need observer.